Let's let u equal some g of x, where g prime of x is continuous over an interval and let's let f of x be continuous over the corresponding range. Let f of x be the antiderivative of f of x, of lowercase f of x. Then we have this relationship, the integral of f of x times g prime of x dx is equal to the integral of f of u du, which is equal to capital F of u plus c, which is equal to capital F of g of x plus c. Okay, so the question becomes, what are we talking about? So let's say we have a problem like the integral of x squared minus 3 cubed times 2x dx. We're going to expand the number of functions we know how to find the antiderivative of. And we're going to start by finding what u is. Let's let u be this inside function. Let's say u is equal to x squared, of course, minus 3. And let's let du, so we're going to take the derivative of u, is going to be 2x dx. We're taking the derivative with respect to u, and so we end up with this dx and the du. Implicit differentiation. Okay, so now if I solve for dx, I see that dx is equal to du over 2x. And why is that important? Well, if we take our original function and we replace what we called u and what we call dx, watch what happens. We get the integral of x squared minus 3 is just u cubed. And then I'm going to replace dx, this is times 2x, and I'm going to replace dx with what we said it was, du over 2x. The 2x's cancel, and what we're left with is this really nice integral of u cubed du. And we know how to find the antiderivative of this. The antiderivative of u cubed du is just u to the 4th over 4. And so if I want to solve my problem in the end, I just replace u with what we know u is, and I get x squared minus 3 to the 4th over 4 plus c. And this should have been plus c, because remember, we're doing differentiation. We're doing integration where we're not really sure what this constant value is. And so we get this answer, and so we have a new set of functions that we can integrate using what we call u substitution. Let's try another problem. Integral of 6x, 3x squared plus 4 to the 4th power dx. Let's let u equal 3x squared plus 4. Then we know du should be 6x, just 6x, dx. Now if I solve for dx, I get dx is equal to du over 6x. This allows me to rewrite the integral u to the 4th power du, because the dx's are going to cancel, and we just replaced what was inside with u. And this integral is just going to be u to the 5th over 5 plus c, and we know what u is, so we replace it, and we get 3x squared plus 4 to the 5th power over 5 plus c. And that's all there is to it with u substitution. As long as you choose a nice u, you have a really nice and easy problem to solve. So what if we had, for example, the integral of z root z squared minus 5 dz. In this case, I'm going to say u is equal to z squared minus 5, which means du is going to be 2z dz, which means dz is going to be equal to du over 2z. Now, when I replace everything, watch what happens here. I have the integral of the square root of u times z, but I'm replacing dz with du over 2z. And my z's here are going to cancel. This is equal to the integral of root u over 2 du. But one nice thing about integration is we can pull a constant out. The constants don't participate in the integration. So I can say this is equal to 1/2 integral root u du, which once again, to remind you what the square root is equal to the integral of u to the 1/2 du. And now we can use our integral rule. Now we can say this is equal to 1/2. The integral of u to the 1/2 is going to be u to the 3/2 over 3/2. When you divide by 3/2, you multiply by the reciprocal, and so this is equal to 1/2, and this is plus c, 1/2 2u to the 3/2 over 3 plus c. And now we can replace u again. We know what we said, u was equal to z squared minus 5, so this is equal to 1/2 2z squared minus 5 to the 3/2 over 3 plus c. And so we can do some pretty complicated functions. We can do some pretty complicated integration using the fact that we can choose a u and hopefully do some kind of substitution that gives us a simpler problem. Let's do one more just for practice. Let's do another similar one to this one where we're going to have to factor something out. Let's try the integral of x squared x cubed plus 5 to the 9th power dx. First, I need to choose my u. I'm going to choose x cubed plus 5, which means du is equal to 3x squared dx, which means dx is equal to du over 3x squared. Now we can replace everything. Integral of x squared times u to the 9th, replace dx, that is very lopsided parentheses, to the 9th. Replacing dx, we get du over 3x squared. We can cross off the x squareds, pull out the 1/3, and this is equal to 1/3 integral of u to the 9th du. Now we just integrate. We say this is equal to 1/3. The integral of u to the 9th is going to be u to the 10th over 10. And remember, if you're not 100% sure if you're taking the integral right using the power rule, you can just take the derivative of this and make sure it comes out to u to the 9th. If I take the derivative, I get 10u to the 9th over 10. The 10's cancel, and we have u to the 9th. 1/3 u to the 10 over 10 plus c. We know what u is, so we'll replace it. This is equal to 1/3 x cubed plus 5 to the 10th power over 10 plus c. And that is our antiderivative of this function. And that is how we use u substitution to solve some of these problems.